Darkness has returned to TechWards. The enchanted chessboard, once a tool for learning, now moves with a mind of its own, spreading chaos throughout the castle.
This is bad. The enchanted chessboard is out of control again.
We need to do something before the whole lab gets taken over.
What if we build something that can outthink the chessboard?
You mean like an enchanted machine?
A magical STM car. It's crazy.
But it might just work, you know.
Alright man, let's build our secret weapon. The TechWards!
And so it begins.
So this is our main page for our Android app. This is the home page. The other two pages include the Bluetooth and the add obstacle page. These make it easy and flexible for the user to navigate through the application. We can communicate with the RPi through the Bluetooth, where we can send and receive messages through our chat function, and it works something like this. So once the image is recognized by the robot during the task, the obstacle ID on the grid is updated to the image ID when the RPi sends back messages to the Android. So here we will notice that the obstacle ID 1 is updated to its image ID, which is 11.
So we can place the board on the grid and place obstacles using two functions. One is directly from the home page, so by toggling the drag and change obstacle buttons, obstacles can be dragged. We can also change the direction of the image on the obstacle by clicking on it. Another way is through the Add Obstacle page, where we can directly enter the XY coordinate along with the direction of the image directly. Both options make the interface quick, effortless, and fun, welcoming every user style. So once the obstacles are set, both the tasks can be started using their respective start buttons in Challenge, and it will reflect on the robot status.
The robot uses the Dublin's path for navigation. It's the smartest path model for vehicles that cannot move backwards. It connects two positions with headings, and only uses circular arcs and straight lines. This ensures smoothness and realistic turns with efficient movement that matches the robot's motion constraints.
So here's a quick demo of our car going through the obstacles and scanning each one of them. So our algorithm consists of multiple parts. The first one is for the TSP. We use exhaustive search since there's only 5 obstacles. Next, we use Reed's shared pathing, which is for Dubin's path with the option of reversing. Then we use rapidly exploring random trees for creating intermediate points along the way. And lastly, we use smoothing, which is a best effort combination of consecutive path segments.
Our system uses multiprocessing on the Raspberry Pi to handle communication, movement, and image processing all at once, ensuring smooth and efficient operation. It starts with the algorithm server, which plans the STM car's route and sends it to the Android tablet, then to the Raspberry Pi for execution. The Raspberry Pi queues up the commands and processes them in order. Movement commands are sent to the STM car, with a mutex lock ensuring no interference during motion. Once an acknowledgement is received, the next command begins. For step commands, the Raspberry Pi captures an image and sends it to the image recognition server. When the image ID returns, it's sent back to the tablet in real time.
For the image recognition, we use the YOLO V8 model, which is accessed through a fast API endpoint. The model performs inference by stepping down the image dimensions for every iteration until a high confidence detection is found. This is done so that the image can still be recognized even if the robot is far from the object. Next, the model draws annotated bounding boxes around the detected image, along with the label of image ID and confidence level. Lastly, we have a collage, which auto-populates the last 8 images together for quick observation.
On the STM side, we had to configure motors and sensors for motion control. For steering, we standardized 90-degree turns because turning radius can be inconsistent for arbitrary angles. Encoder feedback auto-trims left and right power to keep runs straight and drift-free. Sensors are used to measure distance between objects. Ultrasonic handles the front while IR covers side walls. For calibration, I tested fixed interval targets and linearized the readings. Because IR can lag, when required, we move in short encoder-gated steps so it never overextends forward motion.
For task 2, we measured the distance traveled by monitoring encoder values. We tracked the distance traveled by the STM from the point of the first image recognition to the second obstacle. We also added some distance to account for the turning distance. For the turning back to car park part, we tracked the distance traveled along obstacle 2 and then half it to reach the car parks.
And so the STM car was born.
You guys are taking too much time. Let's go!
And so, the chessboard has been defeated. Peace has been restored. For now.